Hello and welcome to an overview of oscilloscopes. Here we have three very different examples of an oscilloscope all connected together measuring the same waveform which is being generated by this signal generator down here. Basically it's a sinusoidal wave at around 10 kilohertz. Also connected is a voltmeter up here, which is effectively showing us that the average voltage that the waveform generator is generating is 0 volts. So an oscilloscope is similar to the voltmeter, except it's going to tell us more information about the signal it's measuring. Specifically, an oscilloscope may be thought of as a voltmeter, which also shows frequency. The bottommost oscilloscope down here is an older analog CRT or cathode ray tube style oscilloscope. This would have been top of the line a few years ago. As you can see, it has many knobs and many buttons on the front. The nice thing about these older analog scopes are that they have one feature per knob. So if you read the labeling on the controls, it's easy to figure out how to operate them. More modern digital oscilloscopes like this one up here offer things like multicolor displays, so they're easier to look at. And as well, they have a lot of text on the screen. So they can take measurements similar to the voltmeter, but they also can do more advanced mathematical features by way of the soft keys. So on a modern oscilloscope, you will have keys that will have multiple functions assigned to them, which will unlock some more potential in the oscilloscope. And then lastly, on the right-hand side, this is a small, inexpensive, portable oscilloscope, which is actually going to do a lot of the same fundamental measurements. It just won't have as many of the advanced features. Battery powered, very inexpensive. That one goes everywhere with me in my toolkit. It's great for field work, and I'll demonstrate each of these to you. If you're unfamiliar with how an oscilloscope operates, when you first approach one, they might appear a bit daunting. But all oscilloscopes share the same fundamental features. In fact, if you can locate and operate 3 controls on an oscilloscope, then you can pretty much drive any scope that's out there. The first primary control to look for on the oscilloscope is known as the volts per division control, or otherwise known as the vertical scaling control. On the analog scope on the bottom, that's this control right here. In fact, it's labeled volts per division. It's currently set at 2 volts per division. If we look at the sampled signal here, we can clearly see that it's deflecting up and down, and there's a grid across the screen. So currently at 2 volts per division, we can measure the deflection of that signal. This exact signal is going plus and minus 5 volts peak to peak. So in total, we have a 10 volt peak to peak signal. If I were to change the scaling on the volts per division, if I were to make it 5 volts per division, then we have zoomed out on that waveform. In fact, we can zoom out even further by changing the vertical scaling. Likewise, we can put it back to 2 volts per division and bring it down to 1 volt per division. So now we're zooming in on the waveform. Of course, now we can't see the full waveform on the screen. So that's the first primary control. You can think of it as the vertical or the y-axis zoom control. The digital oscilloscope in the top here has the same control. It's just labeled differently. They just call it the vertical control right here. Now, this being a digital scope, this is a digital encoder, but it's going to function in the same way. So currently, we're also set at 2 volts per division. We can change this, and now we're reading a 5 volt per division, so we're zooming out on the vertical and zooming out further at 10 volts per division. And we can go the other way as well. Put it back to 2 volts per division and zoom in at 1 volt per division. So the vertical scaling control is what you're going to be able to use in order to look at very small signals and look at very large signals and be able to display both given the size of the screen that you have. Even the small portable oscilloscope over here has the same control. Of course, there's only one encoder in this, so what we have to do is change the function of the single encoder to be our volts per division, and we can zoom in and we can zoom out on that, just the same as the larger oscilloscopes. The second primary control to familiarize yourself with is the time per division or time scale control. On the analog oscilloscope, that's this control right here, and it in fact is labeled time per division. So much like the vertical scaling control, this is going to control the scaling on the horizontal axis or the x-axis. Again, we can change that to zoom in on the waveform or zoom out on the waveform, but again, here on the horizontal axis. On the digital oscilloscope up here, it's labeled as the horizontal control, but much in the same way, if we rotate it in one direction, then we're changing the time per division. That's 20 microseconds per division. Here's 10 microseconds per division, zooming in. And of course, we can zoom out just the same. There's 200 microseconds per division. Our small portable oscilloscope over here can do the same thing. We just have to place the encoder in seconds per division mode. And again, now we can manipulate the encoder to zoom in and zoom out in the time scale. Note that both of these controls, the vertical and the horizontal, on both the analog scope here for channel 1 and channel 2, and then the time scale, and then up here in the digital scope, the vertical and the horizontal controls are physically the largest knobs on an oscilloscope, and you'll find that on most devices. The third primary control to learn on an oscilloscope is the trigger control, and this is a little less intuitive than the vertical or the horizontal control. So triggering is what allows us to view the periodicity of a continuous signal. Another way to think of it is it's essentially a threshold which is going to allow us to lock on to the signal. And on the digital scope, that's this control right here. As I move the trigger control up or down, you'll see a horizontal threshold move. Right now, I can set it to 2 volts. And notice that if I start to reduce it from that, you'll see the entire waveform shift to the right as I'm reducing it. And now as I increase that threshold control, you can see the threshold is moving up and the waveform is sliding to the left. What the threshold control here with the trigger knob is doing is it's aligning the crossing of that signal through that threshold, that horizontal threshold, with the y-axis. That's why it's sliding the waveform right and left. As long as I set the trigger threshold within the upper and the lower peaks of my continuous waveform here, then I'll have a nice, stable, repeating waveform that we can lock into time and view. Now, of course, if we move that threshold beyond where the waveform is, right here, then we'll get something like this. We can't really see what's going on right now because we don't have a proper trigger where we can view a stationary cycle or a few cycles of the waveform on our screen. So if you ever go and try to connect to your oscilloscope and you see something like this on the screen, you should immediately think that, okay, the next thing to do is to adjust my triggering so that I can have a stationary view of this continuous waveform. So you'd come over the trigger control and get it within bounds of the peak-to-peak voltage on that signal. Anywhere in there is fine. And now we have lock onto our waveform. We can also set up the trigger control to view non-continuous waveforms, and I'll show you how to do that in a bit here. But for right now, we'll just consider these continuous waveforms. I mentioned that these are three very different oscilloscopes, so let's talk about some of those differences. Starting with the analog oscilloscope in the bottom here, I mentioned that it does have a lot of buttons and switches, which will allow us to change how the waveform is displayed on the CRT. But one thing it doesn't have is a way to display text. So if we're going to read things like wavelength and frequency and voltages, it won't give us an explicit readout the same way that a voltmeter would. We have to infer them by looking at how many volts per division we have and how much time per division we have, and then counting the amount of divisions that we're deflecting across or up and down with. And that's the way that most oscilloscopes functioned for many decades. The digital oscilloscope up here allows us to program in not only voltmeter and time-based measurements with these soft keys. In fact, right now, it's telling me that the frequency of this sine wave is, in fact, 10.67 kilohertz. But it's also telling me that the peak-to-peak voltage is 10 volts, which is very nice. And it's even giving me a RMS voltage too, which is 3.41 in this particular case. But another difference between all oscilloscopes is going to be what the bandwidth is going to be at the scope, meaning what is the highest frequency signal that we can accurately measure. Here in the digital scope, this happens to be a Siglent. It's telling us right on the tag 100 megahertz. So any signal that we have greater than 100 megahertz, this scope will not be able to represent accurately. Every oscilloscope is a system, and so it is going to have an inherent transfer function to it that is going to have a finite or a limited pass band that it can measure to. And that pass band is going to be defined by several things in the oscilloscope. The first thing is actually not inside the scope. It's going to be the probe itself. So in a typical oscilloscope probe like this, you'll have the ground clip lead, and we'll have the hat here that has a small clip, very handy for latching onto a circuit. And the probe will also have a bandwidth associated with it. This specific probe is spec'd out to have a bandwidth of 200 megahertz. So independent of what the oscilloscope will do, you have to make sure that the probe is not going to be the limiting factor in the bandwidth of the signal that we're able to measure. The second part of the bandwidth limitation is going to be on the circuitry itself. So in the digital oscilloscope case here, we'll have 4 different inputs, 1, 2, 3, 4. Each of those is going to have an analog front end inside the oscilloscope, as well as an analog to digital converter. Those 2 pieces of circuitry combined are going to control what the overall bandwidth of the scope was, in this case 100 megahertz. Same thing on the analog scope, except it's going to be the analog circuitry alone that will determine that bandwidth. But there's a third element, and something that you're going to find in most oscilloscopes that are sold today, the digital ones, is that they also will be software upgradable. So in other words, you can purchase a digital oscilloscope such as this. It'll have a bandwidth associated with it, but you can unlock more bandwidth by purchasing software patches or updates, upgrades to the scope, and perhaps get 200 megahertz or 400 megahertz operation out of them. What that really means is that they're building the superior circuitry into the inputs, both on the analog and the digital side, but you're unlocking those features through the software in them. That's kind of the norm now, and what you'll see on most modern scopes that you'll buy new. We can easily demonstrate the bandwidth limitations of our oscilloscope very simply by looking at a different type of a signal. Let's switch over our function generator to generate a square wave here, and we can see that square wave now represented on each of the three oscilloscopes. We could write a mathematical function for this square wave. If you're familiar with Fourier analysis, we could write a truncated Fourier series that would start at a fundamental frequency, which would be equal to, in this case, 10 kilohertz, and then all the higher order even and odd harmonics generated to create this signal from continuous signals that are sinusoidal in nature. What that means is that we have a very harmonically rich signal being displayed here on each of our oscilloscopes, although it's a very low frequency signal. It's 10 kilohertz. And we can see a nice representation by that. But we know each of these oscilloscopes is going to have a finite amount of bandwidth in order to display this waveform. And we can identify what that bandwidth is if we start to increase the frequency of the test signal. So here we're up at 20 kilohertz. We've doubled the frequency. All looks very nice still. And as we would predict, our voltmeter shows us 0 volts, so that's not very helpful, right? This is why we're using an oscilloscope. We can bring it up even higher in frequency. Here's 50 kilohertz. Bring it up even higher. Now it's getting hard to even see the signal anymore. We're up at 100 kilohertz now. So one thing we can do to readjust is to change our time scale. Now we see our signal again by zooming out in the time domain. We can do the same here. And we can see a fairly nice square wave on these two scopes, and we can do the same over here. But that's interesting. Notice how on our portable oscilloscope, we're not seeing a nice square wave anymore. We're actually seeing a sinusoidal wave. So at 100 kilohertz, we have exceeded the bandwidth of our small, affordable, portable scope. Now, if I were to start reducing the frequency, notice that our square wave, now we're at a trapezoidal wave, so we're in transition back to a square wave, starts to reappear on the small scope, and now we get a nice square wave back again. So somewhere around, here, we're starting to hit the bandwidth of the portable oscilloscope. That's around 44 kilohertz. And then above that, it cannot represent the square wave, all the rich higher harmonics, sinusoidal harmonics that are generated from that. Now we're getting a nice, almost pure sine wave up there. But we're still looking very good with both the larger analog and digital scope. And we can bring it up even higher and higher. Here's 200 kilohertz. And we can bring it up to 300 kilohertz. And at this point, at 300 kilohertz, we can just start to see a little bit of rounding off on the rising and the falling edge of those pulses. But it's minor, and we're still seeing a fairly good representation of our square wave, but we're way beyond the bandwidth of the small portable oscilloscope. So I wanted to make the point here that, of course, you get what you pay for, although you don't have to spend a lot of money in order to get good capability. These used to be very expensive back in the day. Nowadays, you can get a fancy last generation analog oscilloscope used for $100 or $200, just like this. You would probably spend about the same for an oscilloscope in the digital domain, such as this, which gives you nice storage capability, an Ethernet port to communicate with your computer and control it from software in your computer, multicolor display, maybe a 2-channel scope, still for around a couple $100. Still very useful are the small portable oscilloscopes, especially for lower frequency field work. This one I think I paid $20 for from a company called JYE Tech. I think you can get them, and that's as a kit you can build, or you can buy them, I think, fully built for around $50 or $60. So you don't have to spend a lot of money in order to get a useful oscilloscope. Lastly, I wanted to mention a feature that most modern digital oscilloscopes have. If you find yourself hunting around on the controls and not able to properly display a waveform, let's say you've got the vertical scaling kind of off the chart here, maybe the horizontal scaling is giving you something like this. Somebody has changed the position controls around and you're feeling a little lost and you cannot get the waveform on the screen. Most modern scopes are going to give you a auto setup or an auto scale button. On this particular scope that's up here in the right hand corner, it's the blue button right here labeled auto setup. You can think of it as an easy button. So we can hit this, takes it a second, and it is going to intelligently acquire what we have at the input coming through the probe. It'll make some guesses to try to get us in the ballpark of representing the waveform on the screen. Might not be exactly what you would like, but at least from here now, it's easy to go in and fine tune what you'd like to see in terms of vertical scaling and horizontal scaling. There's some secondary controls that some people like to use, especially if you're connecting multiple channels, is to offset the position of each channel. So you can change the vertical position, and as well, you can change the horizontal position of the waveform as well. So a lot of times, the easiest thing to do if you're coming up to an oscilloscope that someone else was just using and things are a little out of whack is to hit that auto scale button, get things rastered into the ballpark that you'd like, and then go and fine tune the controls, the primary controls, to get what you would really like to see between the vertical, the horizontal, and of course the trigger control right here. We can also use the trigger feature to capture the transient portion of a signal. Mathematically, we might handle the transient portion with some exponential term followed by a steady state value. When we were in continuous mode or auto triggering, we were essentially measuring the steady state values of the periodic signals, of the continuous signals. But there are times where we would want to look at a transient event and try to capture it on the screen. So what we're going to do is end up setting the trigger to detect the first time the signal is going to exceed a predetermined threshold, capture that, and then display that on the screen. Let's demonstrate this using channel 1 of the oscilloscope, which happens to be the yellow trace on the screen. Notice that there's no probe attached to channel 1 right now. We're going to start by reducing the vertical control from volts down to millivolts. Now we're at 10 millivolts and all the way down to the minimum setting, which on this scope happens to be 500 microvolts. Now we can clearly see that we're at the noise floor of the oscilloscope. With no probe attached, we're measuring noise at the input of channel 1. The next thing we can do is come over to our trigger control right here. And we had a threshold that was at 0 volts. I'm now going to move that horizontal threshold up and out, maybe just a few hundred microvolts, just to get it up and out of the noise floor. Like this. Now we're still in free running mode. So what we're going to do now is change and place the trigger into single shot mode. So at this point, the oscilloscope is waiting to record any signal that enters channel 1 when the voltage is higher than that minimum threshold of around 300 microvolts that we established. And we can establish that by pranging the input with something metal. So that is basically a demonstration of the piezoelectric effect. We applied some stress to the input jack, the BNC jack right here, and that stress induced a voltage which exceeded the threshold of the trigger threshold. And now we can see that one-shot trigger. So this is recorded in time, and we're just looking at a static picture of that one transient event. We can reset the trigger again, and we can do it one more time. Do it very lightly, so we just have less voltage. We can reset the trigger again, do it a little harder. So in this way, you can capture transients by setting the threshold appropriately and placing it in one-shot trigger mode or single trigger mode as opposed to free running. In this case, we're measuring the piezoelectric effect. And of course, this is only good for one shot. So every time you record the measurement, we have to go back and reset the trigger for the next measurement. Let's measure something more useful by first reconnecting a probe to channel 1. And we can place the vertical scaling back into maybe a couple volts like this. We can also change our trigger threshold up a little higher. On the breadboard here, I have a small circuit where we have a momentary push button switch, which is connected to 5 volts through a pull-up resistor and then ground on the other side. So the 5 volts are being supplied by a 7805 regulator right here. I can turn on that regulator with the slide switch. And we have a little indicator LED that comes on right here. And so now, if I place the scope in single shot mode, it's waiting for a signal to trigger off of. Again, it's a one-shot trigger. And if I press the switch, I can see that we've now recorded the transition from 0 volts to 5 volts from the press of that switch. I can reset the trigger. And now we see the issue with an electromechanical switch. An electromechanical switch is basically 2 pieces of metal that you're pressing together to make an electrical contact. Those 2 pieces of metal have some compliance to them, and sometimes they bounce. So on that second press that I just did, you can clearly see that they came together, some voltage got applied, but then they bounced apart and then came together again. The single shot trigger allows us to capture that event so that we can see the switch bounce phenomenon. We can do a very clean bounce like this. Got lucky, 2 in a row, 3 in a row. Now here, if I zoom in on in the time domain, you can see there also was a bounce, but it was kind of a chattering there, just like this. So every time we press the switch, we get a little different behavior out of the switch. This might not matter if you're just turning on and off an analog circuit, but if this switch was the front end of a digital logic circuit downstream from it, we could end up creating some interesting logic states which are going to end up misfiring when the switch bounces in this manner. Therefore, we need a better way to handle an input such as a momentary switch like this if we're going to drive some digital logic. At the center of the breadboard is a small integrated circuit, which happens to be a 555 timer. And I've built a circuit around that IC to create a switch debouncer, which is basically going to use this physical momentary switch as an input. And it's going to look for that rising edge. So in a way, it's going to act like our threshold control in the oscilloscope. But as soon as it sees that first leading edge of the button press, it's going to create a pulse at the output of the chip, but latch that pulse on. So even if there's switch chatter after the first initial press, that chatter won't propagate to the output of the circuit. And we'll get a nice, clean pulse, which we could use to drive some other circuitry. We can take our other probe here on channel 2 and connect it to the output of the 555 timer. Then I'm going to turn channel 2 on right here. And what I can do now that we're going to use 2 channels is I could move one channel down and the other channel up on the screen, which will make it a little easier to see both at the same time, like this. And we're still in single shot mode. Now, when I press the switch, we're going to see two traces on the screen at the same time. The top one is going to represent the button press, and the bottom one is the output of the 555 timer latching in that button press. This one looked pretty good. Let's reset it and try again. Here we can clearly see that we didn't have a solid press, but we had a nice clean rising edge on the 555 processed signal. Okay, again, some chattering right here, but a nice solid rising edge and positive voltage on the 555 circuit. Here again, we can see how it nicely cleaned up the button press. Okay, so that's a good example of switch bouncing, and then of course switch debouncing using a 555 timer, but most importantly using a single shot trigger on an oscilloscope in order to view the problem as well as the solution. Let's try a different circuit. Okay, we've constructed a new circuit using the 555 timer, which is going to generate a pulse width modulated signal known as a PWM signal. This is what's known as an astable circuit, meaning that it's free running. There is no input switch connected to it anymore, but rather there are several capacitors, resistors, and diodes that are going to create the PWM functionality. There's a timing capacitor, C sub time, and two resistors, R sub A and R sub B, which are going to set the frequency of the PWM pulses. And then there's an adjustable potentiometer, 20K potentiometer, which is going to establish a variable pulse width for the PWM signal. We have our oscilloscope back to automatic triggering so we can watch a continuous signal. And we'll activate the circuit here, and you can clearly see that we have the rising edge of a pulse. We can adjust our horizontal scaling so that we can view that pulse as well as the next ones. So on the screen right now, because we have multiple pulses, the oscilloscope is reading off that we have a 52 hertz signal, and it's in fact measuring the width of one of those pulses as being 1.5 milliseconds wide. And let me readjust the horizontal scaling so we can see that width of just one of the pulses a little bit better. So we have a 1.5 millisecond wide pulse. We can go in and adjust the potentiometer right here, and we can reduce the pulse width down to 1 millisecond wide, and you can see that on the screen. And we can turn the potentiometer in the other direction, and that's going to increase the pulse width to 2 milliseconds. I can demonstrate that again, showing multiple pulses on the screen. The frequency of the PWM waveform is going to stay the same, but each of the pulses that the 555 timer circuit is generating are going to change in pulse width. And we'll set it back to 1.5 milliseconds. The significance of this 50 hertz PWM signal is this happens to be the protocol that you would use to command a servo drive, the type of servo drive for moving around a robot or controlling one of the flight surfaces on a drone. Servo drives are angular position controlled devices. If we would like to command a servo drive to the center point, 0 degrees, we would send it a 1.5 millisecond wide pulse. We can increase that pulse width to 2 milliseconds or decrease it down to 1 millisecond, and that'll give us the full range of motion from plus and minus 90 degrees of angular rotation. A typical servo motor has 3 connections that are brought out through a header. There's the ground connection, the power connection, and the signal connection. So we can take our 555 timer circuit output and connect it to that signal input on the servo drive and command it with this control signal. Here I've connected a small submicro servo to the circuit, and I've mounted it to the front of the oscilloscope with an indicator so that you can see its rotation. And now this is at the center point. We can change the pulse width. We'll decrease it down to 1 millisecond pulse width, and then we'll increase those pulse widths back through neutral, 1.5 milliseconds, and up to the maximum amount, 2 milliseconds. And we can see the servo operating in concert with the commanded signal. The digital oscilloscope has one more big trick up its sleeve. I've put together a circuit to demonstrate it. Again, it's another astable 555 timer circuit, but here the purpose is to generate a square wave. In that circuit, we've got two different potentiometers, a 20 and a 5 kilo ohm, and each of these can be used to fine-tune the frequency and the duty cycle of the waveform. I've adjusted this circuit to generate a 7.3 kilohertz waveform at 50% duty cycle, which is basically making our square wave as we see here on the screen. If we wanted to build this waveform mathematically, we could again consider a summation of Fourier series. Note the Fourier series summation is going to be the addition of a fundamental term and all of the higher order harmonic terms. The fundamental cosine term will have a frequency of 2 times pi times 1 times time divided by the period of the signal. Likewise, the second harmonic term will have a cosine frequency of 2 times pi times 2 times time divided by the period of the signal, and so on and so forth. So we have an increasing frequency of terms. But note at the same time, if you look at the coefficient, back to the fundamental term, the coefficient or the scalar value is 2 divided by 1 times pi. And then the second order harmonic is 2 divided by 2 times pi, and then 2 divided by 3 times pi, onward and upward. The point here is that the higher the frequency harmonic term, the lower its amplitude in its contribution to constructing this overall square wave signal. Keep that in mind as we go forward. Back to our waveform display on the oscilloscope. The screen is telling us that this waveform has a frequency of 7.3 kilohertz and a duty cycle of 50%. Thereby, we're creating a very nice square wave. And so now we understand that we can construct this wave from our fundamental sinusoidal frequency that would match 7.3 kilohertz, as well as the summation of all the odd order harmonics at increasing frequencies. It would be great if we're able to view these harmonics directly in the frequency domain. This digital oscilloscope features a math coprocessor that can do addition, subtraction, multiplication, division, integration, differentiation, as well as a fast Fourier transformation. We can invoke that right here. And now we enter a split screen where we have the time domain at the top still showing our time domain waveform. But now the bottom of this screen is showing us the frequency domain. So low frequency to the left, high frequency to the right, and then amplitude is our vertical axis. On that frequency plot, we can see at the very center, this is the fundamental frequency for our signal that we're measuring. It's at 7.3 kilohertz. And each of these peaks increasing in frequency represent one of those terms in the harmonic series of the Fourier summation. Again, note that as the frequency increases for each of the harmonics, their contribution in amplitude is decreasing as a function of frequency. We can zoom in if we would like in the frequency domain so that we can get a better picture of each of those individual harmonics. And we can zoom back out again as well if we want to view the full spectrum. So this is great. We can see both the time and the frequency domain at the same time by performing some math on the measured signal. We could build a simple first order filter to low pass this signal using just a resistor and a capacitor. That filter would have a transfer function with a cutoff frequency, otherwise known as a -3 dB point, which would be defined by the value of the resistor and the capacitor, specifically 1 divided by 2 times pi times R times C. If we hold the value of the resistor constant, say at 220 ohms, we can swap out different capacitor values, which would in effect shift the cutoff frequency of our first order low pass filter. We can select one of these component combinations, say the capacitor at 0.1 microfarads, and that would set up a first order low pass filter with a cutoff frequency right at 7.23 kilohertz. Effectively the same frequency as the fundamental frequency of our signal. If I insert that capacitor into our circuit, note how things are going to change in both the time and now the frequency domain. It takes a second for the change to be reflected in the frequency domain because recall this is a mathematical process that we're applying to the input signal. In the time domain, we can clearly see that the rising and falling edges of our square wave have been modified. We now have what looks more like a shark fin type signal. As well, in the frequency domain, although we can see that the fundamental portion of the Fourier summation still exists, the higher order harmonics have been reduced. That's the low pass filtering in effect. Mathematically, we can explain this because the suppression of those higher order harmonics in the frequency domain are reducing the ability for the time domain signal to reproduce a nice rising and falling edge. The two are related. There's a nice little trick you can do with the digital storage oscilloscope, and I'll demonstrate that by removing our capacitor first. And so here we can see that we've restored the higher order harmonics by removing that low pass filter, and now we have our square wave back in the time domain. We can save this original waveform here, and I will turn it off temporarily. Now I'll reintroduce the filter into the circuit. And by recalling that saved waveform, I can overlay the original onto the current waveform. So here the original is the blue and the current waveform is the yellow. So here we have a nice comparison in the time domain of the pre and post filter waveforms. If I remove the capacitor one more time, I could choose to replace it with a 1 microfarad capacitor. This would have the effect of shifting the cutoff frequency of the low pass filter down to 723 hertz. For that, I'll use an electrolytic capacitor, which we always have to be careful because these are polarized, so the negative band has to go to the negative terminal. We'll now add this to the circuit and again observe the effects in both the frequency and the time domain. The larger 1 microfarad capacitor has shifted the cutoff frequency lower in the low pass filter. This has effectively implemented a passive integrator. So we're now integrating the input of the filter, and you are seeing our square wave being filtered and processed as now a triangular wave output. There is some associated phase shift from the input to the output, and you can clearly see that there's attenuation because we've implemented a passive integrator. Likewise, in the frequency domain, we can see that the harmonics have been even further suppressed because of the increased filtering. Of course, if we'd like to boost this integrated output signal up, we could add something like an operational amplifier, an op-amp, with some gain associated with it. Okay, let's restore our square wave by removing that capacitor. Very last, a most interesting thing to do would be to see if we could extract the fundamental frequency of our waveform and filter everything else out. We could accomplish this with a resonant second order filter by carefully selecting each of our components to place the resonant peak right at that 7.3 kilohertz fundamental frequency, which would effectively suppress all of the higher order harmonics, but retain the fundamental. For that, we'll have to invoke an RLC filter, which is given by an input to output voltage relationship transfer function, and we can use a corresponding expression for the resonant frequency as a function of the values of the three elements R, L, and C. In fact, when we go to construct this circuit, we only need to use two components. Here's the inductor, which happens to be a 470 microhenry inductor, but it's also going to have resistance associated with it. And if you measure the resistance across both terminals, this particular one is 1.37 ohms. So this one component is going to operate as both the resistor and the inductor in the RLC filter. We can combine that with the previously used 1 microfarad capacitor. We'll bring in the inductor. And connect our scope probe. Right off the bat in the time domain, we can see that we've almost perfectly filtered out the fundamental sine wave. That would represent the fundamental in the mathematical Fourier series summation. So this increased filtering, being a second order filter, has further suppressed the harmonics, but has retained the fundamental frequency right here. And that's what we're seeing in the time domain. Compared with the first order filter, the peak-to-peak value of the residual signal is much larger because of that resonant peak of the filter being aligned with the fundamental frequency. Also interesting is I can hear the resonant frequency of this filter audibly in the room. I'll bring up the other microphone. It's a little irritating because it's at 7.3 kilohertz. But that's in the audible band, so we are hearing this oscillation that we can see in the time domain. We'll turn that down because it's distracting. We can zoom in the frequency domain to take a look at the attenuation of the harmonics. Here's the fundamental at 7.3 kilohertz. That happens to be a value of -4 decibels. And then here's the second harmonic, which is at -24 decibels. So the second harmonic is being suppressed by 20 decibels from the second order resonant filter. Next one over is this one right here. That one is at -34, so 10 more decibels down from the previous one, and so on and so forth. Being a second order filter, we're rolling off those higher order harmonics at 40 decibels per decade. So I wanted to share this resonant second order filter application to extract the fundamental of a complex signal, and I hope you've enjoyed it.